Hi, good afternoon everyone. My name is Tung Lau and I work with Professor Satif Tom here in the University of Toronto. So today I want to talk about how we can use photonic crystal with nanoparticles to enhance solar upconversions. So here is a solar spectrum from AM 1.5. We know that for a solar cell made of silicon, it can only convert photon that is above the silicon band gap. So for photons that is below the band gap, is basically transparent to silicon photon solar cells. So we want to use solar upconversion such that we can fuse two of these sub-band gap photons into one high energy photons that can be reabsorbed by the silicon photon cells. So shown here is a conical structure that is created from our groups. And the upconversion layer will be somewhere sandwiched between this bright reflecting mirror and the silicon photovoltaics, such that any upconverted photons can be reabsorbed by the silicon photovoltaics layers. So the nanoparticles will have a core that is made of silicon, made of erbium, doped with a crystal, such as sodium yttrium fluoride. And on the surface will be some generalized fluorescent agent that sensitize these erbium-doped crystals. And we would like to put these crystals in the upconversion layer that is made of photonic crystal architectures to provide a tunable photonic density of states to change the upconversion frequency, upconversion efficiency. So we examine the properties of erbiums. So erbium is a good upconverter because that is ladder-like energy states with comparable energy differences. So you can take two sub-band gap photons and excite the erbium to higher excited states. And as the erbium decays back to ground state, it can release upconverted photons. And this decay process is mainly radiated because erbium has very low coupling to phonons. However, the absorption strength and the absorption bandwidth of erbium is very narrow. And so we can sensitize the erbium with generalized fluorescent agents as to enhance the absorption strength and the bandwidth. And as shown in this paper, they demonstrate this enhanced upconversion from 800 nanometers to 500 nanometers using bimolecules. And in our work, we would like to get a theoretical examination of this upconversion process, and also we would incorporate a tunable photonic density of states, and such that it can suppress this unwanted spontaneous emission at the first excited state of the erbium, and to boost the efficiency. So here is the energy level diagram that illustrates the upconversion mechanisms. So this is the fluorescent agents. They can absorb a broad band of sunlight to promote to an excited state. And as it decays down to the ground state, it can excite the inner layer of erbium through the Foster energy transfer process. So the erbium can be excited to the first excited state, and with accumulation of population at that first excited state, it can further be excited to a higher state. And this is the upconversion process. And this erbium can also excite this neighboring erbium ion in the inner layers, such that the energy can continue to propagate towards the core of the nanoparticles. And it will diffuse and upconvert until steady state is reached. So coinciding with this Foster energy transfer process are the spontaneous decay. So we would like to use photonic crystals such that it can have a photonic band gap at a sub-band gap photon frequency, such that this spontaneous emission can be suppressed. And at the same time, we would like the photonic density of states to enhance for the upconverted photon frequency, such that it can enhance the expression of these upconverted photons. And for both of these, as we will see, can enhance the upconversion efficiency. So now in our work, we will fix the solar spectrum we cannot change, and also we cannot change the absorption and emission of the erbiums. But we will have present the fluorescent agent as some tunable parameters. So we would, here is the solar spectrum, and below, in between the silicon 10 and 31 transitions, and between the erbiums 10 and 31 transition and the silicon band gaps. So this is the region that we would like to have upconversion. So we would like the fluorescent agent to have a peak absorption to absorb a large amount of this bandwidth of photons. And also we would like the emission peak of the fluorescent agent to coincide with the absorption peak of this erbium 10 and 31 transition, such that it can have a large Foster energy transfer. So once we fix the parameter for the optimized fluorescent agent, we can examine when the simulation examine how it performs. So here the various the dot dash line here is the absorption spectrum for the fluorescent agents, and the solid line here is the emission spectrum, and the top one is the fluorescent agent graph, and the bottom one is the erbium ions graph. And we can see that for the absorption and emission, the rate is roughly the same. That means that the sunlight is once it's absorbed by the fluorescent agent, will basically emit without transfer into the inner erbium. And this is the case without any photonic crystal. So we can see that the emission of the erbium is 3 orders of magnitude that is smaller than that of the fluorescent emission of the fluorescent agent. So now if we have the photonic crystals such that there is a photonic band gap in this in the environment of these nanoparticles. So we see that the emission spectrum of the fluorescent agent is given by this purple line. That is much reduced compared to the case without photonic crystals. And this reduction of emission means that the energy has to go somewhere, and it is transmitted into the erbium. So we can see that from this emission line of erbium, it is much enhanced compared to the case without photonic crystal. And also, the emission spectrum of the erbium, we can see that it is above the silicon band gap. That means there is a large amount of upconversion that is happening in these erbium ions. So what happens if we have further enhancement of the photonic density of state at the upconverted frequency? So everything here is roughly the same, but not shown in here is that there is a much reduced phonon transition in the fluorescent agent. But we can see that for the erbium ions, there is a much enhanced emission at the upconverted frequency. And so we see that with this structure, once suppression of photonic density of state at the subband gap frequency and enhancement at the upconverted frequency, we can much enhance the overall upconversion efficiency. So this is the definition of the internal upconversion efficiency, which is the number of emitted upconverted photon from all the erbium ions over the absorbed number of photons absorbed by the for one fluorescent agent. So the maximum of this frequency is 50%, meaning that we need 2 subband gap photons to upconvert to one high energy photons. So here we look at the relation of the photonic density of state with this quantum efficiency. So we see that there is a general increase if we increase the depth of this photonic band gap until the band gap is roughly 2 orders of magnitude suppression from the erbium case. I mean, this density of state is normalized over erbium. So that means that we need a structure that can provide a depth of like 2 orders of magnitude of photonic band gap photonic density of state suppression at the subband gap frequency. And then once we have this photonic band gap, we can enhance further enhance the efficiency by introducing this enhancement in the photonic density of state at the upconverted frequency. And again, we aim at the 2 order of magnitude of this density of state enhancement in order to saturate this frequency efficiency enhancement. So lastly, we look at the practical issues. So here in the fluorescent agent, besides the spontaneous decay, there is also the non-radiative phonon-induced transition that is compatible with the Foster energy transfer. And we examine how this will affect the efficiency. And we find that in order for this principle to work, we will need the non-radiative phonon decay to be comparable to the spontaneous emission rate of the fluorescent agents. And for dye molecules, most of the dye molecules have a very large phonon-induced transition at the infrared. And so we are looking at some other materials such as germanium nanocrystal as the fluorescent agent. And so here is a conclusion. We can use a fluorescent. Yeah, here's the conclusion. So we see that with a fluorescent agent, we can enhance the absorption bandwidth and cross-section of the erbium crystal. And here we give some optimized parameter for this generalized fluorescent agent. And by using a photonic crystal, we can introduce a band gap and then enhance photonic density of state to increase the upconversion. So is there any questions? Thank you.
Usually, the efficiency of the upconversion is very small.
Yes.
So, what is these particles, for instance, that we're talking about? We're publishing this Nature Photonics paper. They have a few percent quantum efficiency.
Yes.
So, how much are you increasing that?
How much an increase compared to
the particle without the photonic without?
Oh, yes. Say this is the case without any photocrystal, and it is roughly like 10 to the minus 4, the efficiency. And then this is with photocrystal is like 10 to the minus 2, so it's like a 2 order magnitude increase.
Do you want to calculate how much power conversion is it for years or?
Yes. So this what we talk about 5% internal quantum efficiency, not external.
Okay, so there's no questions. The same speaker again.